To start graphing this piecewise function, I'm going to start with drawing my boundary walls for the top piece. So my boundary walls are going to occur at -3 and 0. Something special will happen at my graph at those locations. So let's draw a sort of dashed line, this invisible barrier wall at -3, where x is -3. And then here's that same line, or similar line, when x is equal to 0. So something special will be happening at those locations. So let's begin by graphing, well, what's going to happen in between there. My piecewise function says the graph is going to behave like the line 2x equals 5 in between those two boundary walls. So let me begin by making an xy table, as we've always done when we're graphing these piecewise functions. You can do slope-intercept form, but sometimes it's tough depending on where the piece is existing. So I always want to include the boundary points in my xy chart. So I'm actually going to include -3 and I'm going to include 0. But then I'm going to make a note of whether the graph can or cannot exist at those points, depending on the inequality. And so it says that -3 can exist there. X can be greater than or equal to -3. So I'm just going to make a note in my chart that this point will be a filled-in circle. 0, on the other hand, x has to be less than 0, so it can't quite get there. So again, I'm just going to make a note in my chart that this will be an open circle for this point. And then since I want at least 3 points to graph a line, I need to pick any point in between there. So -2 would be great. Anything between 0 and -3 would be fine. So let's go ahead and plug these x values into that top piece of our piecewise function and see what our output is. So 2 times -3 gets its -6. If I add 5 to that, I get an output of -1. You guys can figure this out. My next output value would be +1, and if I plug 0 in for x, 2 times 0 plus 5 will get me 5 as an output. Okay, so let's go ahead and plot those 3 points and see what this piece of my graph will look like. So -3, -1, and notice how I count -3, I'm on that wall, so I want to be careful in checking my notes. My notes told me that I can actually be equal to -3, so I do have a filled-in circle right there. Make that point really big so I can tell that it's a filled-in circle. My next point was -2, 1, and -2, 1, and that's just a point on the graph, so that can be just any size you want it to be. And then my last point was 0, 5. That's also on the wall. Checking my notes, 1, 2, 3, 4, 5. Checking my notes, I saw that's an open circle. I can't actually be equal to 0, so there's a hole in the graph. Connecting those gets me the first piece of my piecewise defined graph, a segment right here. Okay, let's go ahead and take a look at the next piece of the puzzle. This time I have, again, 2 boundary walls between 0 and 2. So I already have a wall at 0. Let's go ahead and draw another dashed line in here at 2. So something else is happening between there. And according to this piece of the piecewise function, well, it's constant. Whatever's happening between there, the output is always going to be -3. So I've got just a horizontal line. I mean, I can do an xy table if I want to. And again, if I'm, picking 2 values at the endpoints. And then I note this time, those are both filled in circles because 0 and 2 are both included in the domain. And picking any number in between there, 1 is a good choice. But it's kind of irrelevant because it says no matter what you pick for x, the output no matter what is always -3. That's what gets you the horizontal line. So between these next 2 boundary walls, I just have a horizontal line. So I'm going to count down 3 spaces. I'll include 2 filled in circles to say that those are included, and then I'm just going to connect those with a horizontal line. So there's the second piece of the puzzle. Let's get to the final piece. Notice this time, for the final piece of this function, it's anywhere where x is bigger than 2. So this will be a ray. This will go on forever. I don't need another boundary wall. It says the graph will behave like the line -2x if x is bigger than 2. So in my xy table, I'll include 2, the boundary point. And then this time, since it has to be greater than 2, there's a hole in the graph right there. So I'll have an open circle just in my table to make note of that. And then I need to pick 2 numbers, at least 2 numbers bigger than 2. So how about 3 and 4? Fantastic choices. Plugging those values in for x in this bottom function, then I get -4 as an output, -6 as an output, and -8 as an output. So let's plot those points and finish this graph out. So 2, -4 is a point. Notice it's on the wall, so consulting my notes, I see that that was an open circle. Make it really obvious. My next points would be located here. I could use my slope of -2, if you know what's going on with slope, to find those besides just plotting points, but oh well. Since there's no boundary wall when I draw my line, it begins there and continues forever in that downwards direction. And so there is a lovely looking piecewise defined function. To answer their questions at the bottom, is the domain all reals? That question means if I go left or right on the x-axis, will I always be able to find a point above or below me? And this time, unlike the other two videos, the answer is no, because if I pick an x value somewhere in this location, there's no graph. The functions don't tell me what to do if I pick an x value smaller than -3, so the domain's not all reals. Is the function continuous? Can you draw this without picking up your pencil off the paper? Yeah, no way. So this is definitely not going to be a continuous function.